All right, welcome to section 4.9. What I want to do here is I want you to pause this real quick and read these three statements. All right, pause it. All right, so if you read them, you're going to notice that in all these examples, velocity, that's a rate, variable rate, knows the rate. These are all rates. And again, our rates come from derivatives. And all the three examples are trying to go back to their position function that we had talked about. So now we're going to be looking at antiderivatives, which is kind of like working backwards. So if you remember when we first started with f of x, think of f of x, we write it down. Then right below that, we wrote down f prime of x. We did the first derivative. Then we did the second derivative. And we could do the third derivative. And we kind of line these up directly below f of x, then f prime of x, and so on and so forth. Well, what we want to do is we want to start down maybe at, let's say f double prime of x. And we want to go back to f prime. We want to start building up. We want to work backwards up to the original f of x. And we do that by doing antiderivatives. All right. So the problem is to find a function, we'll call it capital F. This way it tells us we're working backwards, whose derivative is known. And we're going to call that, say, function f. Now, again, you could think of it in reverse. You could call that f prime, and capital F could be just called f. But I'm going to stick with the same notation as the author. If such a function, capital F, exists, it's called the antiderivative of f. So write a function, capital F, whose derivative is f of x equals 3x squared. So that's like saying, okay, we want to build a function working backwards. So here is my power rule for a derivative. So here the n is the 3. The n minus 1 is all 2. So I can see, wait a minute, if I'm going to work this backwards, I need to take the 3 that I moved down from the exponent, I need to move it back up on top of the exponent. So my f of x, capital F of x, would be x cubed. Or some teachers will call it the antiderivative f, we'll just call it capital F, that's easier, is x to the third. And an antiderivative of f of, wait a minute, hold the phone. What about our constants? Our antiderivative function, capital F of x, could be x to the third plus 4. Because remember, when you take the derivative of a constant, that's a 0. So you could have x to the third minus 5. You could have x to the third plus 100. You could have x to the third minus 1,000. X to the third plus 10,563,284. Whatever constant you want, because when you take the derivative of that, it's a 0. So the general form for our antiderivative function is going to be capital F of x equals x to the third plus some constant. So we're always going to add on a plus c. And that's what our theorem is saying right here. And again, c is going to be any arbitrary constant. So the process of finding the antiderivative is called antidifferentiation. Man, I wish I could get all the tiles to play that in Scrabble, let me tell you. All right, it'd be an instant win. All right, find the most general antiderivative of each of the following functions. Okay, so if f of x equals sine of x, we're kind of building this backwards. So I'm going to look, I need my derivative rules for sine and cosine. So the derivative of sine of x is cosine x. Derivative of cosine x is negative sine x. Okay, so we're starting on the right side, wanting to build what's on the inside of the brackets. So here's sine, but we don't want our sine to be negative, so this negative is going to have to be put on the cosine of x. So capital F of x equals negative cosine of x. Oh, wait, and plus c. Don't forget your plus c. I'm telling you right now that will be worth 1 point on every question on the test. I kid you not. I have taught this many times. I have seen many people forget the plus c and lose 15 points on a test because they forgot the stinking plus c. It's the easiest points you can get. All right. F of x equals 1 over x. Okay, so I'm thinking that is when I take the derivative of my natural log of x. So we're working backwards. So capital F of x. Wait a minute. Hold the phone. Wait a minute. We got to stop and think. Domain problem here. The domain for the natural log of x is 0, infinity. The domain for 1 over x is negative infinity, 0, union 0 to infinity. It's missing half of the domain. So if we're going from the 1 over x to natural log of x, we have to be able to obtain both of those possibilities. So my capital F of x is going to look like a piecewise function. So when x is bigger than 0, that's this part, then the natural log of x plus c, we'll call it sub 1 for the first one, will be my f of x. Now, how do I get the negative x's over here? Well, the natural log of negative, now my x is negative, so a negative times a negative will be a positive, and then plus that c sub 2. And that's for when, again, your x's will be negative. So this is not negative x because this is x is less than 0. The x value that goes in here is negative. So we have two negatives being multiplied together to make a positive. Well, I tell you what, I'm not going to waste my time with this notation here. How do we guarantee it always to be positive? Let's just call it the natural log of absolute value of x, and then that covers both of these situations. And then don't forget, plus c. All right, f of x equals x to the n power, where n cannot be equal to a negative 1. Because if it was equal to negative 1, we'd be back to this situation right here. All right, so we're going to be working our power rule backwards. So we start with x to the n. That's x to the n plus 1 minus 1. And if you recall, when we take the derivative, we take the n plus 1 out to the front, and we subtract the 1 from it. All right, well, if I want x to the n here, I got to divide by the binomial n plus 1. All right, so we take away the n plus 1 and the minus 1 up in the numerator, and that's the derivative of this function that gives you x to the n. So the antiderivative of x to the n is what we have in brackets here. So this is kind of our power rule for doing the antiderivatives. So we're going to add 1 to the power, and then, come on mouse, and then divide by that new exponent we created. And then don't forget, plus c. All right, anti-differentiation formula. So remember we had that whole sheet of derivative rules we had to learn. Well, now we got to do them all backwards. So if my function is k, then that's a constant. So taking the derivative of a variable x, let's say 2x, and I take its derivative, that gives me the constant 2. So working backwards, we're just going to make x to the first divided by 1, plus c. If I have a k being multiplied to the outside of my derivative function, it stays there, and we just now make a capital F, the antiderivative function, plus c. If you add and subtract your functions, again, think of these as being derivatives, then that's just going to be capital F, the antiderivative of f of x, plus or minus the antiderivative of g of x, plus c. And we just talked about the power rule working backwards. We said that was x to the n plus 1 over n plus 1 plus c. Nobody forgets there's plus c. And again, that's never when x equals negative 1, because that's that function up here, 1 over x. Remember when we were taking the derivative of e to the x and it was just e to the x? Well, guess what the antiderivative is going to be? E to the x. But with a plus c. 1 over 1 plus x squared should look familiar to you. That's your inverse tangent derivative. So working it backwards, that's going to be the inverse tangent of x plus c. This too should look familiar. That was your inverse sine of x derivative. So the derivative of inverse sine of x was this. So if we start here, take its antiderivative and work backwards, we go back to the inverse sine of x, but again, plus c at the end. Oh, I already did my natural log of x. The mouse is jumping ahead of me here again. We looked at this example earlier. That's going to be the natural log of x plus c. Okay, sine of x, its derivative is cosine of x. But if we want to go backwards, you saw that example, it's got to be negative. All right. The antiderivative for cosine of x will be sine of x, because think of sine of x, take its derivative, you get cosine. Secant squared, that's your tangent. You take the derivative of tangent, you get secant squared. Again, we're just working backwards. Cosecant squared, I believe that was cotangent x, but again, that was the negative. Remember those negative rules on all the co-functions. Secant tangent of x, that was your secant of x plus c, but here's cosecant cotangent negative cosecant of x plus c. So again, to obtain the most general antiderivative, so when I want general form, you have to put the plus c on all your answers, just like we did here in the table. All right. Find the most general antiderivative of each of the following. So please pause the video and find the antiderivative of each of the terms. All right, welcome back. So here, 3 to the x is 1. Work it backwards. All right, keep the 3. All right, now add 1 to the power, which is 2, and put 2 in the denominator. X squared over 2 is the antiderivative of the x. Now you can multiply the 3 to it. 3x squared over 2 plus c. For b, hopefully you change this to a negative power, so we can use your power rule in reverse. So I add 1 to the power, take that new power and put it in the denominator. So adding 1 to negative 2 is negative 1. Put that in your denominator, x to the negative 1 over negative 1. And then let's put that in the denominator so we have a positive x down here, and then the negative 1 either goes to the top or you put the negative off to the side. It's fine by me. But don't forget, plus c. For c, we should do each term separately, just like we did the 3x to the first over here. Put a 1 on your x, you unpowers there, so you get the pattern. So the 3, the minus 5, and the plus, in parentheses, you're just looking at the x. So let's add 1 to the 4, divided by 5, x to the 5th over 5. Add 1 to the 2, divided by 3, x to the 3rd over 3. Add 1 to the 1 is 2, divide by 2. There you go. Found all the variable terms first. Now let's multiply their coefficients in here. So this will be 3x to the 5th over 5 minus 5x to the 3rd over 3 plus our x squared plus c. That's your antiderivative f of x, or capital F of x. All right, pause the video. Ooh, work these out. Remember what you got to do with signs in here. All right, welcome back. Square root of x, probably want to write this as x to the 1/2 when we were finding derivatives. Now we're working backwards. Add 1. That's going to be 3/2. So I divide by 3/2. But we don't really divide by fractions. We multiply by its reciprocal. So 2/3 times x to the 3/2, then plus c. And remember to get your variables to match. So if they give us a g, it becomes capital G. All right, f of x is equal to 2 sine of x. All right, as we saw earlier, sine of x, its antiderivative was negative cosine of x. And so now it's 2 times negative cosine of x plus c. Remember your constant 1? You just put x to the 0 there, add 1, divide by 1. It's just 1x or x plus c. All right, example 3. Find all functions g such that g prime of x is equal to 4 sine x plus 2x to the 5th minus the square root of x over x. Notice that the direction said all functions. That's plural of g. That means you're going to add on the plus c. All right, so here we go. I'm going to take my 4 sine of x plus 2x to the 5th, and I'm going to divide it by x. I'm separating this fraction here into 2 separate terms because I want to do the power rule backwards on these. And I'm going to simplify these. So x to the 5th divided by x to the 1st is x to the 4th. X to the 1/2 divided by x to the 1st, that's 1/2 minus 1 is negative 1/2. Now we can go ahead and take the derivative of each of those separate functions. So 4 times, we'll do the antiderivative sine of x, plus 2 times, we'll do the antiderivative of x to the 4th, minus, then we'll do the antiderivative of x to the negative 1/2, and then we put in our plus c. So the antiderivative of sine of x is negative cosine of x. I'm going to do a lot of these so you can get those signs squared away. All right, add 1 to the 4, divide by 5, x to the 5th over 5. Add 1 to the negative 1/2, that makes it positive 1/2. Divide by 1/2, or multiply by its reciprocal. We're going to multiply the 2 back up to the top. So clean everything up. G of x is equal to negative 4 cosine of x plus 2x to the 5th minus, there's the 2 multiplied to x to the 1/2 plus c. Or another option is to change the x to the 1/2 back into the square root. They're both fine by me. I know the author in WebAssign, I believe they like the square root version of this. All right, extra examples. Find the most general antiderivative of each of the following functions. Again, pause it, practice it, come back when you get A and B done. All right, welcome back. So here again, separate this as to 2 different terms. Change your square root of x to x to the 1/2. Subtract your powers, or here, we'll move this up to the top as a negative. So subtracting our powers gives us x to the 1/2. Bring up the 1/2 as minus x to the negative 1/2. All right, so now we apply the power rule. Add 1, makes that 3/2, divide by 3/2, or multiply by 2/3. Add 1, divide by, makes that a 1/2, divide by 1/2, or multiply by 2 over 1. So there's my 3/2, my 1/2 on the bottom, but again, we're going to change it and multiply the reciprocal of 3/2, 2/3, to our x to the 3/2, multiply 2 over 1 to our x to the 1/2 plus c. Again, if you want, you can change that back to 2 times the square root of x. All right, for g, we have sine of x over cosine squared of x. What I would do here is break your cosine squared x down to 2 cosines in the bottom. Here's my thinking. I see sine over cosine, so one of these I can change to 1 over cosine of x times sine over cosine, which makes this into a tangent, and 1 over cosine will change that into a secant. Now that's easier to use. Okay? All right, so my g of x, secant x times tangent of x, that's the derivative of secant of x. So my capital G of x, or my antiderivative of g of x, is just secant of x plus c. All right, so I'm going to stop here and we'll bring back part 2 in just a minute because I want to keep these videos short.